But in my perspective, it's not right to leave the school. That's my perspective. It could be wrong because I have also.
True, but then
Yeah,
we're trying to like do something better economically, because then
yeah,
there's
that is.
university and all that stuff. So
Yes, of course.
whatever's, I mean, we'll do it only if a lot of people who are like knowledgeable in this field will agree to it. Only then.
Yeah, that's true. That's true. I agree, but it's different for everybody. I can't really um, say what's right for you.
And plus, like for most of my school life, I guess till grade 10, I was always doing stuff like that, like athletics and
Hmm.
extracurriculars. So it's okay, it's over.
For 1 year, yes. The university would be cool, so that's fine. Okay, then. So, the first law of thermodynamics is what we're going to do today.
Wait for 1 second. Could you go to the second experiment?
Second one. This one?
Yeah.
Yeah, okay.
Yes. So here, sir, we do T2 minus T1. But then we said that T1 and T2 is constant. So is it going to be zero value for the T2 minus T1?
No, why 0? If it's like, say, 30 degrees and it's like 50 degrees, so for both of them, it is going to be 20 and 20.
Okay, so I mean in both the readings, this has to be same.
Yeah, in both the readings, the change has to be the same.
Oh, okay, I misunderstood it. Sorry.
Okay, no problem. So now, first law of thermodynamics is pretty tricky actually. So, first of all, we should understand that it states, wait, it states that the increase in internal energy of a system equals the sum of heat supplied to the system and the work done on the system. Now, this basically it's more of a English, say, test because you need to basically read it very carefully. So, first thing that you need to understand is that the increase in internal energy is due to if the sum of heat supplied to the system and the work done on the system. Now, this means basically internal energy, the change in internal energy is denoted by U. You already know this from the previous chapter. So, if there is an increase, it has to be due to heat being supplied to it plus the work done on the system. Now, I'll tell you basically this means increase in internal energy. This is heat supplied to the system. So you need to look at the prepositions and work done on the system. Now, why I want you to highlight these because there could be different cases, right? And I'm going to tell you what cases there might be. So, for that, we're going to make uh, a nice looking table. Pick one. Okay. And six. So, okay. Never mind. We'll increase the size if it's needed. Okay. So, right here, right here positive and right here negative. Then let's look at delta Q, and then let's look at delta U, and then let's look at work. So when the equation that I've written up, which basically is how the internal energy changes, the portion where the heat is given, right, or taken, doesn't matter. So you need to understand, you need to put a positive sign only when heat is supplied to the system, and if it will be negative if heat is lost by the system. So which means is that if heat is going into the system means that object that we are looking at, so the internal energy is going to increase. If the heat is going to increase, they're going positive, and if it goes out of it, it will be negative. Internal energy will be positive when there is an increase in internal energy. So the sign in the equation will tell you. And if there is a decrease in internal energy, then it is going to be negative. Like that. For work done, when work is done on the system, that's when work in the equation will be positive, and when the work is done by the system, it will be negative. Is it clear, everybody? In the equation, really. Now it's pretty simple that if you let something cool down, right? So the heat energy is going to go out of the system, which means that the heat energy is going to be negative. If you heat it up with a Bunsen burner or something, it means that it is going to gain heat, which means that it is going to be positive. Internal energy is simple, it depends on both of them. But what about work? So I just want to tell you that if the system is compressed, when I say compressed, means that the volume decreases. When the volume is reduced or decreases, it means the work done is done. And if the system is decompressed means that it is allowed to increase the volume, so the volume increases, then and only then we could say that actually work will be positive or negative, like this. Is it clear, everybody? Just want to tell you.
Sir, could you repeat that once?
Yes. What I'm saying is, suppose there is a balloon, right? Like this. If you compress the balloon is going to get smaller in size, right? It means work on it will be positive in the equation. And if you allow the balloon to get bigger, like bigger, so basically how would it get bigger? Because now it is doing work on the surroundings, not the basically work is not being done on the balloon, but it is doing work on the surroundings. So basically the work done will be negative with respect to the system. Is it clear?
Yes, sir.
So that's why I wrote compressed and decompressed. Now, so let's do one example and try to figure out what I mean. So it says a motor does 2000 joules of work on its surroundings, okay, while releasing 3000 joules of heat. So it says determine the change in internal energy. Okay. Now I'm going to write the equation. The general equation is delta U is equal to delta Q plus W. By just looking at the statement, how much would I put plus next to the heat or negative? What do you guys say?
Negative. Negative.
Negative. So basically, this means because heat is being released outside to the surroundings, it means it is negative. And motor does work on its surroundings. So positive or negative work?
So negative.
Negative, because the work is not being done on the motor, but it is being done by the motor. That's why it's like my negative. So the internal energy is going to change by minus 5000 joules. Is it clear? So you have to basically read the prepositions, and if the preposition that I've written here, whatever matches that, you need to put a negative or positive sign. Is it clear?
Yes.
Now it is very important to understand this with respect to gas laws. And you might have already done gas laws in O levels. And gas laws were like, the first law, if you remember, was the Boyle's law. The Boyle's law basically stated that pressure is inversely proportional to volume provided temperature is kept constant. Do you guys remember this law?
Yes, sir.
So it means is that pressure is inversely proportional to volume provided temperature is constant. And with respect to it, you might have also learned about P1V1 equals to P2V2. You learned it in ideal gases as well, remember?
Yes, sir.
Now, if I want to draw a curve, so I just want to tell you that inverse curve basically is a downward curve. So if I put pressure on this side and if I put temperature on this side, volume on this side, so it is going to show you a curve like this. It is an inverse curve, okay? What it means is that basically all the points, suppose this is A, this is B, this is C, this is D, this curve basically shows you an isothermic curve. Iso means same, thermic means thermal, which means that all the points in this line have the same temperature. Let me write it to that. All points on this line has the same temperature. Is it clear, everybody?
Yes, sir.
Now the biggest question is, how does this isothermic change? How does this isothermic change affect first law of thermodynamics? So we know that delta U is equal to G, delta Q plus W, right? If the change in temperature on this line is 0, and we know that internal energy was equal to 3 by 2 nk delta T. You remember this formula?
Yes, sir.
If the delta T is
Yes.
0, then the change in internal energy will also be 0. Which means that if I put like 0 on this side, then it will be change in Q plus W. So an equation means that the heat energy will be equal to minus work done. Is it clear?
Sir, could you repeat the last sentence because your voice broke?
So if the change in temperature is 0, then if I put it back to this equation really, so you see that here there is 0, so W will go there, it will be the heat will be equal to, the change in heat will be equal to minus W. Is it clear? Now,
Yes.
if you look at this minus sign, basically this minus sign indicates that work is done by the system, and you can actually see this from the graph as well, because if you see from A to B, the volume is increasing, and if the volume is increasing, it means that basically it is doing work on the surroundings. That's why the work done is negative. Do you guys understand this?
Yes, sir.
So what you do is, when you supplying the heat to the system and you want to keep the temperature constant, so the only way you can do that, if you let the system to expand, and if you're expanding the gas, it means its volume is increasing, which means that the work done is negative. Is it clear, everybody? I think I should write it down too, because you might forget it, because they might ask you. So as a gas is heated, molecules gain kinetic energy. Okay? Since we want temperature to be constant, let me write temp instead of this, temperature to be constant, right? We would allow the gas to expand. Hence, gas would do work on the surroundings. That's why there is a negative sign, right? Is it clear? Of course, it would change to positive when, if the gas is cooled. If the gas is cooled, the gas is going to contract. If it contracts, then of course the sign would switch to positive. Is it clear? Automatically, you don't even need to do it, because if the heat from the gas goes outside, a change in Q will be negative, so negative will cancel out with the negative with W, so it will automatically be positive. Do you guys understand this now?
Yes, sir.
Now, the next law we are going to discuss, it is called Charles' law. So most of you might not have done it, because I think it was not part of the syllabus back then. It's still not part of the syllabus in O levels. So it states that volume of an ideal gas is directly proportional to the temperature. Now, provided the pressure is constant. So it means that this volume is directly proportional to temperature provided pressure is constant. Okay. Now, the whole basically system basically believes, like, here, let me show you this. So you got to have temperature on this side, volume on this side, and when you draw anything directly proportional, it should start from the origin like this. So there is a line. Let me make it a steeper line just to give you another perspective later. So you might see that basically here, let's call this P, Q, R and S. This sort of change basically refers to isobaric change. Isobaric change basically means at all points on the same line, pressure is constant. Is it clear, everybody?
Yes.
Okay. So now I will also ask you one more question. Okay, Balke, let's wait for it. Should I ask it right now or should I not ask it? I don't know. Let's ask it anyway. Okay, so if I draw another line, okay, on the same diagram, just to show you something like this, a lesser gradient line. So let's say this is A, B, C and D. Now they have different gradient, right? So if I say this is pressure 1 and this line was at pressure 2, which is constant, but they will have still some value of pressure, right? So I want to know, can you please tell me which of the line shows that it has greater pressure than the other one?
E2.
P2 will have higher pressure?
No, I'm just guessing. I don't know.
So
Okay.
P1.
P1 will have higher
P1.
pressure. Okay. That's incorrect. P2 is correct. I'll tell you why. By the way, if the meeting ends, which is about in 1 minute 30 seconds, you got to rejoin. So P2 will have greater pressure than P1. The reason for this is that basically PV over T is equal to the constant. We already know this. And if I make V the subject, you'd realize that basically K upon P is equal to like this. Can I write it like this, please? Now, if you compare this, right, this is y times mx, y equals to mx, right? So the gradient here of the line basically is equivalent to k, which is a constant, over p. So the higher the gradient is, the lower the pressure is going to be. So because P1 has a higher gradient, it means P1 has lower pressure. Do you guys understand this?
Sir, could you repeat it?
Yes. So basically I rearranged this equation in terms of V. So we made V the subject, okay? Because V is on the y-axis, right? And I compared, you see that V is on the y-axis. A straight line from the origin in math is V, y is equal to mx. T is on the x-axis, right? So that would mean that the gradient is equal to k upon p, right? If you look at gradient and p, they are basically inversely proportional to each other. Okay, so what I was saying, that if you look at the gradient, which is k upon p, so p and gradient are inversely proportional to each other, which means that if the gradient is higher, then the pressure will be lower of that line. Is it clear?
Yes, sir.
That's how I know. Understood?
Yes.
Okay, so we can actually do something to this as well. I want to do this as well. Let me draw another line. So suppose there is another line here as well in the previous diagram, just to, this P, Q, R and S. So this is suppose T1 and this is T2. Can you tell me which line has a higher temperature?
T1.
No,
T2.
T2.
But sir, there's no slope, right? So how do we compare it with the straight line equation?
You can't, but you should understand that both pressure is directly proportional to T and the volume is also directly proportional to T. So higher line would mean that basically when the pressure is high and the volume is also high, it means temperature would be high. That's why they have, higher pressure at the higher volume. Do you understand?
Yes, sir.
Do remember that, and this one too. Any questions now? Should I go forward? Now, this change, basically we want to see that how does this isobaric change affect the first law of thermodynamics. Okay, so we know that actually the equation is Q plus W, like that. Okay, so this is our principal equation. Now remember this, in this one the pressure is constant, right? So energy supplied, temperature is also changing, so internal energy will have some value. But this time work done will be written as pressure times change in volume. Do you guys remember this equation?
Yes, sir.
This was basically the first equation we did from when we started this, remember? And I said this equation only works for constant pressure of work done, because right now the situation is that in Charles' law the pressure is constant. That's why we can replace work done with pressure times change in volume. Understood? Any questions?
Yes.
Okay. Now the last law. The last law is the pressure law. Now pressure law states that pressure is directly proportional to temperature, provided that volume is kept constant. So whenever you're comparing like these three things, so when you compare two things, the third one has to be a constant. So pressure is directly proportional to temperature, provided that volume is constant. That it means. So if I draw a graph of it, so this will be pressure in pascals, this will be temperature in kelvins, and now if I make a line just like this, and write P, Q, R, and S. All of them have the same volume on this line. And if I make another line, just to make a comparison, A, B, C, D. So this, let's call this V2, let's call this V1. Now I just want to tell you that this sort of change is called isometric change, which basically means related to length, which means all points on the same line have constant volume. Is it clear, everybody? Or the same volume? Now, if I ask you now, which line has a higher volume, what would you say? Which line has a higher volume?
V2.
Are you sure? Look at the equation again. The equation we made.
V1.
Pressure and volume are inversely proportional. So, Suha, this has to be V1 will have higher volume than V2. How do I know this? Again, I'm doing this. PV over T is equal to K, right? Now I need to make P the subject. If I make P the subject, this is going to be K times T over V. Now compare it with Y is equal to M times X. P is on the Y axis, T is on the X axis. So the gradient is equivalent to K over V, which means higher the gradient, lower the volume. Is it clear?
Yes, sir.
Okay. Now,
So the question, like for the previous graph, it was which has a greater pressure, right?
same rule. Higher gradient, lower
No,
pressure.
the question was which one has a greater pressure or temperature?
In the previous one, like this one,
Yeah. Yeah.
Charles' law. In Charles' law, I asked which one has a greater pressure. So I wrote P2 is at greater pressure than P1.
Right.
Also, you can just look at it. See, volume and pressure are not really fond of each other, right? So, if you look at the y-axis where the volume is, the line which is farthest away from the y-axis would have the highest pressure. Do you understand?
Yes, sir. My brain just glitched for a second.
Yeah, and same goes here. The line which is farthest away from the pressure axis would have the higher volume because they're not, they don't like each other. Is it clear? Just like that.
Yes, sir.
Okay. Now let's combine all of this, and I just wanted to show you something. Okay, so for that I will copy this for just a reference. I want to show you something interesting that is happening right here. Okay. So I'm just going to write all changes together, and this will help you basically interpret what type of change is happening when they're going to give you a graph. So for that I want basically this line to be moved a bit here. Okay. And this removed. Now imagine this, right? If I suppose if I go from A to B to Q, right? And then Q to say D. Okay. Think about it that Because T2 was higher than T1, so if I want to increase the temperature, what kind of change is this? You guys tell me.
Sir, I didn't get your question.
Again, there are two lines given to you. Okay, let me just erase all these points. It's not required really. I say the temperature T2 is greater than T1. Okay. They say there is a point A, and then the gas particles basically go to a new state which is T2, like they increase the temperature, and then come back to this. So this is say M, and this is D. Is it clear? So this is given. Okay. Now I want to know what is really happening between A to M. What kind of change is this? Who's going to tell me?
Work is being done by the system.
No. You're right, you're basically right. But I want to tell you what
Sir,
kind of change. There are
isobaric change.
three changes: isobaric, isometric, isothermic. What change?
So isobaric.
Isobaric. Why? How do you know?
So the pressure is same.
Because between A and M the pressure is same. Do you guys understand this?
Yes, sir, now I do, after the
Okay.
answer. Because I was like, I didn't know what to say at
Okay.
all. I thought of saying isobaric, but then
It's alright.
I was like, okay, temperature and
Okay.
stuff.
So in here, if you look at it, the temperature, the change in temperature has increased. Don't you think so? You guys understand? Now,
Yes, sir.
between M and D, if I ask you what type of change is this, what would you say?
So isometric.
Isometric. Why?
So volume is constant.
Because between M and D are exactly at the same volume. Do you guys understand now?
Yes, sir.
Okay. Gatika, Rafi. Who else is there?
Yes,
Fatma
sir.
is here? Fatma, are you here? Oh yes, Fatma is
Yes.
also here. Okay. Fatma never talks to us. And now, what about A to now? From this to this, can I say that the temperature has basically the change in temperature is negative because temperature falls, right? It goes from higher to lower, right?
Yes, sir.
So from A to D, what type of change is this? A to D. What is happening?
Sir, isothermic.
Isothermic, because the temperature is same. It is T1, right? Now
Yes, sir.
think about it this way. Now I'm going to give you another perspective here. Suppose this was like 300 kelvins and this was like 600 kelvins. So it means that basically it goes to, when it went to A to M, basically the change in temperature was plus 300 kelvins. Do you agree?
Yes, sir.
And then when it went from M to D, so it goes from 600 to 300 again, so the change in temperature was minus 300 Kelvin, right?
Yes,
So
sir.
if I say what happened to A, M, and then D, you would say actually there is the change, overall change in temperature is zero, hence internal energy increase was zero. Do you guys understand this?
Yes.
Yes, sir.
Interestingly, whether you go from A to M or M to D, or you go directly from A to D, you would actually realize that the change in temperature is zero and the internal energy is zero. So, what do you learn from this is that if you reach the same temperature after one or many changes, change in internal energy will always be zero. Do you guys understand this?
Yes, sir.
Anybody who did not understand this, please let me know.
Sir, can you explain again?
Yes. So between, you see, A to M, when we went there, so we jumped from 300 Kelvin to 600 Kelvin. So the change in temperature was 300, right? From M to D, we jumped from 600 to 300. So basically, the change was negative 300, right? If you add the temperature in that process, so plus 300 on this side and negative 300 on this side, so at D, the total temperature change was 0. Do you understand? So, or if you go from A to D directly, you don't go to M, you just go A to D directly, still because they're at the same temperature, so the change in temperature, like at A it was 300, D it was 300, so change would also be 0. Do you understand?
Yes.
So what I'm saying is that no matter which path you take, whether you go from many changes or you just go through one change or whatever, if you reach the same point on the same line, it means the change in internal energy would be 0. Would you remember this?
Yes, sir. But could you explain the part and like the changes in the graph?
Okay.
Like I didn't get that.
Change in the graph. Okay. You see, Soha, when you were at A, what is A's temperature? 300, right?
Yes, sir.
What is M's temperature? 600. So when you jump from A to M, what is the change in temperature? Plus 300, right?
Plus 300, yeah.
So now M is 600, D is 300. When you go from M to D, what is the change?
No, like temperature wise, I get it, but you know how we were like deciphering it was if it was isobaric or metric or
Okay.
that part.
Okay. Now, for that, you need to realize that actually A and M lie on this same line. You see?
Yes, sir.
This is just one pressure. So it means if you go from A to M, the pressure is constant.
Right.
So it is an isobaric change. Do you understand? Iso means one pressure, only single. Okay.
Yeah.
Now, if you go from M to D, so M and D are at the same volume.
I get it now.
So it is
Yeah,
isometric. And if you go from A to D is same temperature, so it's isothermic. Understood?
Right.
Okay.
Yes, sir.
Now let me give you like one definition, and then I'll give you one more question, and you'll realize that basically what we have done here, basically you'll do the question just in a second. So one more process which is like rarely, I don't know, it's never asked, but they never said we won't ask, so we have to do it. Adiabatic process. Now this is a funny one. Adiabatic process means that a process that occurs without the transfer of heat or mass between the system and surroundings. Now, what it means is that if there is no heat exchange happening within the system, so when you write the equation delta U delta Q plus W, it means that in adiabatic process, delta Q will be 0 because there is no exchange of heat anywhere, which means that delta U will be equal to just the work done either on the system or by the system. Is it clear, everybody?
Yes, sir. Yes, sir.
Okay, very good. Now we do the question that we were waiting for. I show you how to deal with those. So, question 1. So, I'm going to show you 3 type of questions, and one by one we are going to look at them. So, they have given you a graph like this, and they have shown you a point P to Q. So this is P, this is Q, goes from P to Q, then it goes from Q to R like this. There's another process they've shown where they say it goes from P to S and then S to R like this. This is the process. Okay, so they say this is the process 1, whatever is happening. This is the process 2 in the second, it's a green line. This is pascals, this is volume. Okay, now they've given it. They say if 8 joules of heat is absorbed by the gas while 3 joules of work is done on the surroundings, by the gas in process 1. Now, determine the amount of heat exchanged in process 2 if 1 joules of work is done by the gas in that process. Okay, is it clear, everybody? Now, if you look at the whole situation, that they start from P, both the processes, and end up at Q. Do you understand what I'm saying?
So they end up at R.
End up at R, sorry. So both basically start from P and end up at R. So if I say that no matter where you begin, if you end up at the same point from, like you start from the same point and end up at the same point, what did I tell you about that just now?
Internal energy is 0.
Internal energy is 0. It means that the change in internal energy in process 1 is 0, and it is the same case with the change in internal energy in process 2. Do you guys understand this?
Yes, sir.
Now, check this out. No matter what, the change is the same, right? Whether it's 0 or whatever. So, we can write that basically delta Q plus W will be equal to delta Q plus W on both sides. In the first process, it says 8 joules of heat is absorbed by the gas. Should I put positive 8 or negative 8?
Negative.
Negative 8. Negative. Are you sure?
Is it positive?
Positive. Why positive? Because it is absorbed by the gas. Do you understand? Heat is received. Is it clear, Kartika?
Yes.
Then it says, while 3 joules of work is done on the surroundings by the gas. So, positive work, negative work. What do you say?
Negative.
Negative, because it is done on the surroundings. Okay. Now the next process. It says determine the heat exchange. So we want to find this while 1 joule of work is done by the gas in that process. What should I put? Negative 1 or positive 1?
Negative.
Negative 1. Now you guys understand this. Okay. So you solve this. 8 minus 3 is 5. And 5 plus 1 joule. So the heat received in process 2 would be 6 joules. Do you understand this? Simple, right?
Yes, sir.
So the idea is that if you start from the same point, end up at the same point, it means that both processes have the same change in internal energy. Whether it's 0 or not, it doesn't really matter. But the thing is that it's like this whole thing is same. So I wouldn't particularly write 0. It could be a different value, but the change will be same. 0 is when they come up to the same point. Is it clear, everybody? Any question? Any question you have? Let me know.
Sir, what if the
What if the sorry?
Sir, what if the internal energy isn't 0 or same?
Isn't 0 or the same? It would have been possible if pink one would have reached R and the green one would have just reached S. Then it would be different, and you wouldn't be able to, equate them then. Got it?
सर उस तरह का क्वेश्चन आ सकता है?
हाँ, इसी की तरह के क्वेश्चन आते हैं एक्चुअली.
Okay.
What do you do
अच्छा
in that
अच्छा,
situation?
यू से कि
Because
उस तरह का क्वेश्चन आ सकता है. नहीं, उस तरह का नहीं आ सकता. दैट्स टू हार्ड फॉर यू टू डिटरमिन. यस.
Sir.
सॉरी.
Never mind.
Okay. So now I don't know if I give you that question or not. I don't know. Let me think about it. Well, I needed to do 4 questions with you total, but okay. It's 3 minutes left to my next class. I think we should stop now, and we will continue this tomorrow. All right. Okay, please do revise it a bit because this is a tricky